This video covers a topic that I'm calling Interpolation of Sampled Data. I hope you find this as interesting as I do, and we're going to see how the sampling theorem can be used as an effective tool for interpolating sampled data. This topic is going to be important for our 4PAM communication system, and it turns out we're going to be using the results from this lecture to develop an optimal sampling time algorithm for symbol synchronization. But I'm also hoping you make a mental note of the topic in case you ever run across applications where you need to, in fact, resample data. Okay, it turns out this comes up in several areas. For example, resampling or some other form of interpolation of data often arises in data science applications. So it's important beyond just our communication application. All right, so as I mentioned, we're going to use this a little bit later on to do symbol synchronization. So we'll apply the results in the next part of the course. Okay, so let's start with what I'm calling a thought experiment. All right, so here we have some data. It's sampled data. All right, and one of the things that we can assume is that we are sampling a band-limited process or band-limited signal. And we can also assume that we're sampling fast enough that the sampling rate is 2 times f max. All right, so I actually did that. I created a signal that's band-limited. I sampled it at 2 times f max, and I produced a plot of a few of these samples. Okay, so if you'll notice, just to get your self visually aligned here, down on this axis I have the sample value n. So here is sample number 10 is a 0, sample number 11 is this sample, 12 is here, and so forth. Okay, and so my question for you is, how would you connect the sample values? That's one way to think of it. Another is, how would you fill in the gaps where you think that's what the actual signal would be, based on the sample values? So think about that for a second. All right, one thing you might think of is saying, well, do like a plotting program. MATLAB, if you gave it samples and you said plot it, it would connect the samples with straight lines. Okay, and if our samples are close enough together, we could visually represent a signal where it looks good. In class I've often mentioned, for example, I've changed the upsample factor on some of the applications, and the reason I've changed it is so I can get plots that look good. All right. Okay, so if you connect it with straight lines, this would be what you would get. And so if you wanted to find a certain fractional sample value, so let's say we know what 13 is. 13 is this sample. What is 13.5? Well, if we interpolated with straight line interpolation, we would get something around this value for 13.5. Okay, so that's one thing we could do, but that's not very pleasing because we know that we're sampling a band-limited signal, and so we know it shouldn't have these sharp edges on it like we're seeing. And so let's erase that and try something else. Okay, if we tried something else, we would be thinking, the ideal reconstructor of a sample data system is actually going to try to put smooth lines through these samples. Okay, so it might look something more like this is how I would kind of guess how it would go for the signal. All right, at least smooth lines instead of jagged straight lines. Okay, so that looks a little better, but our brain is not really that good at doing this task because we want to connect the dots a little bit more simplistic than what would actually happen if you applied sampling theory. All right, so hopefully this gives you some context of the problem, and you've probably seen applications like if you took a thermal class, you often interpolate values from a steam table. Well, you know, those points are collected really close together, so linear interpolation on a set of data sometimes makes sense, but sometimes it does not. I wanted you to be aware of that. Okay, so that's it for our thought experiment. Let's turn to the signal that I actually used. Okay, it turns out I used sine instead of cosine. It turns out to generate that plot, I used an easy signal and I wanted it to be representative. It's representative in the sense that it's a band limited signal. All right. In fact, we know the exact frequency is 100 hertz. All right. So the 100 from here. It was sampled at 250 samples per second. And so if I zoom in a little more closely, here's sample 15, that's a 0. Sample 16, that's right here. Sample 17 is right here. Okay, so you see the the sine function fills in these gaps. All right. I say it fills in the gaps. It's, that's where it came from. So that's really not accurate. I took this sine function, I sampled it to get the sampled data. Okay, so what we would like to do is say that we didn't know this came from a sine function. We don't know what values that should line up on, but we do know that the information is there because we've sampled a band-limited signal. We've sampled it fast enough. We should be able to reconstruct any sample value between samples. For example, if I wanted sample number 16.5, I should be able to put that into a certain algorithm and get something that's really close, probably even as close as I wanted. You could make that argument, as close as I wanted to the sample value at 16.5. Okay, so that's the problem we're trying to solve. Okay, so it turns out that according to sampling theory, we can reconstruct all the signal values that are between samples. All right, and so let's take a look at what we know about sampling theory. All right, with sampling theory, we know that we started with just the samples, and conceptually what we can do from there is form the impulse train signal. Okay, so we take the sample values, we multiply by an impulse train. Every cap t, we get a new impulse. We add all those together and we get this signal xs of t. All right, so I've drawn that here. It's got impulses in red, and what I'm trying to depict there is that the impulse heights the weight of the impulse is given by the signal value. All right, so we put this signal into the low pass filter and out comes x of t. All right, so just samples here. Out comes the full known value of the signal for any value of t, even those between samples. All right, so that's the idea. We're using sampling theory. All right, so you can do the math on this. All right, we know what the impulse response of a low-pass filter is. It's a sinc function. Okay, we're seeing that here. Here's a sinc function. So I put the sinc function in. I get the samples. I sum those together, and I actually can come up with the mathematical expression for the ideal interpolator. All right, so you give me all the samples. All right, you tell me what value of t you want. Plug into this expression. And do the, here's a problem, infinite sum, and we have the values. All right. So it turns out that there's problems with an infinite sum, but we can approximate that. All right, if we are just looking at a certain value of t. For example, let's say that the value of t looks like the following. We take t to be a certain n naught value. All right, so I've talked about an example here where I was looking at 16. Let's say n naught is 16, and then we want to know the fraction of a sample. So t is the sampling interval, so tau times t equal 0.5. That would be the fraction of a sample. Okay, and so I could do sample number 16.5 by letting n naught equal 16 and tau equal 0.5. All right, so by that I'm interpolating between samples. I'm getting sample 16.5 instead of sample 16. All right, so what's useful for me to do there is I need to convert these infinite sums to something that I can actually do. And so what I know is that the sinc function falls off over time. And so when I plug in these values, I'm noticing a mistake here. That should have had a cap t with it, and so should have this. Okay, so that's fixed up correctly. But when I plug in to the value of t, I get the sinc function here as this signal, and effectively what I'm getting is samples, equally spaced samples of the sinc function sampled with an offset of tau. Okay, so I can do that. I can get that data, I can form this finite sum, do this calculation, and I get an interpolation. All right, so let's relate that back to this example we've been working on. So first of all, the TB MATLAB code. The TB MATLAB code has a function called interp_sync. All right, and what you do with interp_sync is you put in x. These are the samples that you use. Okay, you put in the value that you want to interpolate. So for example, we said we wanted to find the t equals 16.5. Okay, between sample 16 and 17 is 16.5. Okay, and then L is going to turn out to be the number of data samples that you use before sample 16 and after sample 16. Okay, so I have the samples marching along like this. Okay, I come up on sample 16, then there's sample 17, and I keep going. This is the sample axis. Okay, I want sample 16.5. I need the x values, L samples out in front and L samples behind. So x is an ongoing vector of data. I need these samples in front and behind. Okay, and if I plug that in, if I plug in the whole data sequence, I'll have that. Okay, and I just need to specify what value of L I would use. Okay, he uses this parameter in this code called beta. Beta comes from the square root raised cosine pulse, which happens to be at beta equals 0. The square root raised cosine pulse is a sinc function. All right, so I'm not sure why I even had that as an option. In my opinion, you should always use beta equals 0 for this application. Okay, so from there in the code, what he does is he calculates this parameter called t now. T now is what I was calling n naught. Okay, so you round that to an n naught value. So if t were 16.5, t now is round 16.5, which is 16. Okay, and then tau is the fractional part, so 16.5 minus round t is 16, so that would be 0.5. All right, so we know t now and we know tau. All right, this gives me the sinc function, and This particular line is just a fancy way of doing the summation that you need to get the ideal interpolator. All right, and so then you pick off the proper value coming out of the convolution, the proper value coming out of the sum, and you get the interpolated value. Now, I realize that was skipping a lot of the mathematical steps, but in my mind, what I think of is that code implements this ideal interpolator. All right, I don't need to know everything inside the black box to make that work, although I could figure it all out if I wanted to. Okay, so how do we apply this code to do the interpolation like we had talked about at the very first part of this video? All right, so let me set this up for you. This is still continuing on our example. We have a sampling rate of 250. We take 60 samples of sine 2 pi 100, essentially t, right? We're sampling it, so t is equal to n over fs. Okay? All right. I wanted to also generate the actual signal. We're going to interpolate, and then see how close it is compared to the actual signal. All right, so I have a signal called yt and a time vector t. Obviously that's sampled as well, but you can see it's sampled at a much higher rate so that you get a nice, pretty plot of sine of 2 pi 100 t. Okay, the rest of this is just things I needed to do to make the plots look good. And so what you need to know from here is that we are going to do interpolation. And the way we're going to do that is we're going to look at n equals 16. I'm calling it ns for samples. ns equals 16, and this code says go 16, 16.1, 16.2, all the way out to 20. And so you see we're getting the actual sample values, which are the integer values, right? 16, 17, 18, 19, and 20. But we're also getting these fractional components of a sample, and they're going to show up as y-interp. All right, and then we're going to plot each one of those onto the plot that we've already generated. All right, and so we'll be able to see how well this interpolator does in finding out the real value of the signal. Okay, so here's the output. All right, so you can see we're stepping here. We started at 16, here's sample 16. At 16.1, notice that the point falls right on the curve. 16.2, we're falling right on the curve. So this interpolation does a really good job as long as you have plenty of, well, as long as you're sampling faster than the sampling rate and you have enough data where you can get, you know, in this case I used, if you go back and look at the code, I used L equal 12. So we needed 16 plus 12, you know, so we know it needed the sample values all the way out to x28. And then 16 minus 12, we needed the sample values all the way back to x4, x of 4. So as long as you have data in front of and behind the value that you want interpolated, you can do this. You can use this sync algorithm to find out the exact answer. All right, so you notice in here, we only used the samples. This only was the samples. We never used the fact that we know what the underlying signal was in this particular case. All right, so hopefully that will mean something to you. I find this to be a really interesting result and a little bit mind-boggling when you go back and look at the beginning where we're like, how would we put the smoothest curve possible through these data points? Well, it turns out the low-pass filter does that job for you, and because it's doing that, it's actually interpolating all the data between the samples, and you can use that in communication applications and data science applications and other applications where you might be sampling a band-limited signal.